Hello everyone, welcome to the session on fluid power systems. I am Satish H, Assistant Professor, Department of Mechanical Engineering, Maharaja Institute of Technology, Mysore. So in this session, we are going to discuss, we are going to start the second module, that is the pumps and actuators. So the topics which I am going to cover in this session are listed out here. The first one is the pump. Here we will in brief try to understand what is mean by the pump, how it is like used in the hydraulic systems, and then how does a pump work. So and then the second one, the topic is a classification of the pumps. Okay, so the pumps are classified based on various criteria that we will see in detail. So how the pumps have been classified. So and then the third one, pumping theory of positive displacement pumps. Okay, so under this heading we will discuss the construction. With an example we will try to understand how does a pump work. So with the help of a piston pump, which is a type of the pump, so we will try to understand how the construction and working of a pump. So and then in the next one, the construction and working of a gear pumps. Okay, so gear pumps are used, okay, when two gears are meshing with each other, and then they kind of create a pumping action. Okay, so under the gear pumps we have various other types of pumps. For example, we have an external gear pump, and then we have a lobe pump, internal gear pump, and then G-rotor pump. Okay, for all these types of the pump we will try to understand how the like what is the construction and then the working principle of all these types of the pumps. Okay, so coming to the first topic, that is pumps. Okay, so what do you mean by the pumps? Okay, pump is the device, okay, which is a heart of an hydraulic system. We know that in an hydraulic system it is made up of various components which are arranged in certain fashion in order to do the desired work or desired application. So like for example, we have a pump, and then we have an actuator, and then we have a control valves, different types of control valves, pressure relief valve and flow control valves. And direction control valves, okay, and then the tank, and then the piping system. Okay, among all of them, okay, the pump is called as a heart of an hydraulic system, which is a very important component which drives the fluid through the hydraulic system. Okay, so what happens inside the pumps? Okay, so basically the energy conversion happens inside the pumps. Okay, the input energy to the pump is mechanical energy. Okay, so and then the output energy is the hydraulic energy. Okay, a pump is a device which converts the mechanical energy into the hydraulic energy. Okay, the mechanical energy is supplied to the pump via a prime mover. Okay, normally we use electric motor in order to drive the pump or input the like mechanical energy to the pump. At the output we will get the pressure energy or fluid energy or the hydraulic energy. Okay, so during the pumping action, so a partial vacuum is created. Okay, we have kind of inlet and then outlet in the pump. A partial vacuum means the pressure which is less than the atmospheric pressure is created at the inlet of the pump, due to which, okay, due to the pressure difference at the inlet of the pump as well as the tank, the fluid is taken to the inlet of the pump. Okay, so due to the mechanical action, the fluid is thrown out to the outlet of the pump. Okay, that is how the energy which is the mechanical energy is converted into the hydraulic energy. Okay, so that is a brief introduction to the pumps. And then the second topic that we are going to discuss is the classification of the pumps. Okay, so this is the broad classification. In detail, the pumps are classified in such a way. So basically we have pumps, and then they are classified into two types. One is non-positive displacement pump and then positive displacement pump. Okay, so these are the two important classification of the pumps. Okay, let us try to understand what you mean by the non-positive displacement pumps. Okay, so non-positive displacement pumps are used, okay, so they develop, okay, less pressures, whereas for higher volume flow rates, okay, we can use this non-positive displacement pumps. Okay, since they have developing a lesser pressure, pressure, but in the case of hydraulic circuits or a fluid power systems, we need a higher power generating or a higher pressure pumps. Okay, so they are less useful, okay, in the case of a hydraulic systems or a fluid power systems. Okay, so but they find their applications in transporting a fluid, okay, from one place to the other place. Okay, for example, in the irrigation system you can use this kind of the pumps, okay, because from the source you have to transfer it to the irrigation fields, okay, then you can use this. Okay, or you can use these kind of pumps in the case of a water distribution to the households. Okay, so at your homes, okay, in order to lift the water from the sump to the overhead tank, you can use these kind of pumps. Okay, so that is the non-positive type of like a displacement pumps. Among them we have a centrifugal pump, axial pump, and then the radial pump. Okay, so centrifugal pump is most widely used, okay, where it consists of a impeller and then outer we have a casing which is a volute casing we call it, because the cross sectional area increases radially, okay, towards the outlet. Okay, so these pumps, when the water comes into the or passes onto the impeller, okay, they throw out these water particles or the water, okay, outwards, okay, with the help of a centrifugal force. Okay, so that will create a pressure at the outlet. Okay, so that means we get the hydraulic pressure or the hydraulic energy at the outlet. Okay, so that is called as a centrifugal pump here. Okay, so and then next coming to the positive displacement pumps. Okay, so the positive displacement pumps, okay, like related to this subject are in a fluid power system or in a hydraulic systems. Okay, these are very widely used pumps in a hydraulic systems. Okay, why? Because, okay, they can sustain very high pressures. Okay, so in the hydraulic systems or the fluid power systems, okay, so it has to, we have at the actuator end, okay, so we have to lift the load, and then when the fluid is passing through the pipelines, the friction is also developed. Okay, so against this friction and then the load, the pump has to work. That means it should have a higher hydraulic power or the pressures. Okay, so in the positive displacement pump we can get that higher pressure, so these are useful. Okay, so for the fluid power systems. Okay, so in the case of a positive displacement pumps, okay, for each revolution of the shaft, okay, it displaces, okay, it discharges a fixed quantity of the fluid into the hydraulic system. Okay, so I repeat, for each revolution of the shaft, okay, a fixed quantity, okay, of the fluid is discharged into the hydraulic systems. Okay, so in this case we have certain advantages over the non-positive type. Of course, one is higher pressure compared to the non-positive type of pumps, and then positive displacement pumps has a very high volumetric efficiency. So and then they are very compact in size. Okay, you have a very lesser size, you can make a pump which is of a positive displacement pumps. Okay, so that is a difference between the non-positive and positive type of pumps. Okay, so they are broadly classified, positive again classified into the rotary pumps and then the reciprocating pumps. Okay, so what do you mean by the reciprocating pumps? Okay, so in the case of a reciprocating pump, we kind of have this piston and cylinder arrangement. Okay, so when the piston is reciprocating inside the cylinder with the help of a prime mover, okay, so a suction is created at the inlet of the pump. Okay, so and then the fluid which is taken from the tank into the cylinder is pushed out at higher pressure. Okay, so with the help of a mechanical action. Okay, it is basically a piston and cylinder arrangement we have. Okay, that is called as a reciprocating. Reciprocating means the cylinder is reciprocating inside the cylinder, that will create a pumping action that will convert the mechanical energy into the hydraulic energy. They are classified as axial piston pumps and then the radial piston pumps. Okay, so axial piston pumps are when the piston and then the pistons are arranged. Okay, so in the cylinder axis is same. Okay, then we can call it as a axial piston pumps. Okay, so there we have inline piston pumps and then the bent axis piston pumps. Okay, so in the case of a inline piston pumps, okay, so what happens is we have kind of a driving shaft that will give the mechanical energy to the pump. Okay, the axis of the driving shaft and then the axis of these pistons, okay, are in the same line, they are parallel. Okay, so they are coaxial. Okay, that is why it is called as a inline piston pumps. Okay, so we have one more kind, that is a bent axis. Okay, what do you mean by the bent axis? Means the axes are not same. Okay, they are not inline. Okay, they are not coaxial. Okay, so axis of this driving shaft and then axis of the what do you have, piston and cylinder, they are at the inclined position. If I take this hand as a driving shaft axis, if I take this hand as an inclined position, which is axis of this cylinder and piston, okay, they are something like this, okay, they are not in a parallel position, whereas they are in an inclined position, okay. So this inline, again they are classified as variable plate, okay, and then inclined swash plate, and then cam and shaft driven, okay. These are the types of the inline type of a pumps, okay. So similarly we have a radial piston pump. What do you mean by the radial piston pump is, we have a kind of a circle, okay, the pistons are arranged in the radial direction, that means around a circle we have a piston arrangement. Those type of pumps, okay, so are called as a radial type of piston pumps. They are like classified as a stationary cylinder block and then the rotating cylinder block, okay. In the case of the stationary cylinder block, the cylinder in which the pistons are rotating, okay, they are not, the cylinder is not moving, okay. So in the case of a rotating cylinder block, the cylinder block which has the pistons also rotates, okay. So that is the difference between stationary and then the rotating cylinder block, okay. So again coming back here, rotary pumps, okay. So here those are also called as a positive displacement pumps, okay, but whereas we have a rotation, okay, of the elements of the or the components of the pump, that is why they are called as the rotary pumps, okay. So we have a gear pump, vane pump, and then the screw pump, okay. So in the case of a gear pumps, we have two gears, okay, which are taken inside the casing. When the one of the gears is rotated, okay, so it will create a negative pressure or the vacuum pressure. So because of the difference of pressure at the inlet and then at the reservoir, the fluid is taken in, okay. While rotating of the two gears takes place, the fluid is taken, okay, like between the teeth of the two gears, okay, towards the outlet, okay. That will create the higher pressures, that is called as a gear pumps, okay. So similarly we have vane pumps, which is also a classification under rotary pumps, and then the screw pumps, okay. So in the screw pumps, what we have a two idler screws, okay, and then basically we have three screws, among which two are idler screws. Between those grooves of a screws, okay, the fluid is moving from the inlet to the outlet, okay. So that is called as a screw pump. And then vane pump, again classified as a fixed displacement and variable displacement, okay. So we try to understand what you mean by the fixed displacement and then the variable displacement, okay. So as I said, in the positive displacement pumps, you like for every revolution of this the shaft, a fixed amount of fluid is thrown, okay, or like output into the hydraulic system, okay. In the case of the fixed displacement, for every revolution, if it is like 1 liter is going out at the outlet, okay, for every revolution of the shaft, okay. So it is constant for every like you take the 10 revolutions, 10 liters is going out of this outlet like outlet of the pump, okay. Whereas in the case of a variable displacement pump, you can vary this the displacement, okay, per rotation, okay. So whatever the fluid which is coming out of the pump, you can vary that, and that is why it is called as a variable displacement pumps, okay. So again we have this fixed displacement pump are classified as unbalanced and then the balanced type of vane pumps, okay. So this is a broad classification of how the pumps are classified. They are basically classified as non-positive and positive, and then again sub classifications, okay. It is a detailed classification of the pumps. Okay, now let us discuss the second topic, third topic, that is pumping theory of the positive displacement pump, okay. So this is a sketch we need, we will try to understand with the help of this sketch. So what do you mean by the pumping theory is, okay, due to the mechanical action, so we have a vacuum pressure is created at the inlet of the pump, okay. So we know that at the tank, okay, where it is open to the atmosphere, so there is atmospheric pressure. Due to the pressure difference at the inlet of the pump and then the tank, okay, the fluid is, okay, taken or pushed into the inlet of the pump, okay. So after like whatever the fluid which is taken inside the pump, okay, is pushed back into the outlet or into the hydraulic system, okay, again with the help of a mechanical action. So in order to understand this pumping theory, we have taken this a positive displacement pump, okay, that is a piston pump. So construction wise, it consists of a cylinder along with the rod here, and then which is reciprocating within this cylinder. Okay. So and then here we have didn't show this prime mover. A prime mover is used to move this piston and a rod assembly. Okay, that is the mechanical energy we are inputting there. Okay. So and then we have a two vents, okay, or the valves, the valve number 1 and then the valve number 2. This is the inlet line and this is the discharge line. Here the fluid, high pressure fluid, goes to the hydraulic system. Okay. Here the fluid from the tank is taken from the, okay, I mean fluid to the inlet is taken from the tank. Okay. This is the tank. We have a vent, okay, which is on the surface of the oil here. Okay. Atmospheric pressure is acting. Okay. So this is the oil tank here. Okay. So the coming back to the operation, how does it functions? Okay. So when the prime mover, okay, starts to operate, okay, this piston moves towards this side, that means to the left side, I mean onto the right side actually. So the volume inside this cavity 3, okay, the 3 number I have represented for this volume. Okay. So the volume inside this is increases. When the volume increases, okay, the pressure drops here. Okay. So when the pressure drops, okay, this is at the lesser pressure than the atmospheric pressure, and then at that time this valve is closed and this valve is open. Okay. So the fluid which is in the tank, okay, due to the difference in pressure starts to lift, okay, starts to come to the inlet of this a piston pump here. Okay. So after this piston starts to move, okay, in the opposite direction, okay, it pushes the fluid whatever which is inside this cavity 3, okay. At that time this valve is closed and this valve is open. Okay. Whatever the fluid which is taken, okay, during the suction stroke is like discharged into the hydraulic system here. Okay. So by this method we are converting the mechanical energy which is given with the help of a prime mover is converted into the hydraulic energy or the pressure energy or the fluid energy, okay, at the outlet here. Okay. So this explains the pumping action. Okay. So basically here we create the vacuum, okay, due to the mechanical action, the vacuum pressure is created at the inlet of the pump, but the tank fluid which is at the atmospheric pressure, due to the difference of the pressure, the fluid is taken to the inlet. So in the suction stroke, okay, so in the retraction stroke, so the whatever the fluid which is taken, okay, it's pushed back into the hydraulic system which is at very high energy. Okay. Now let us go to the next topic, that is construction and working of the gear pumps. Okay. So as I said before, the gear pumps are the positive displacement pumps. They at the outlet for every revolution of the shaft, okay, the output or the discharge is a fixed volume of fluid is discharged into the hydraulic system. Those are called as a positive displacement pumps. Okay, under which we can classify, while discussing the classification we discussed that they are classified into gear pumps, vane pumps and screw pumps. Okay, so in this session we are going to cover the gear pumps. The gear pumps are classified, okay, as external gear pumps, lobe pump, internal gear pump and then the G rotor pump. Okay. So here on the board you can see this the two types of the pumps. The first one is external gear pumps and then the lobe pump. Okay. So here in the case of an external gear pump, okay, so by meshing of the two gears, okay, so the pumping action is created. Okay. So coming to the construction of this external gear pumps, we have two gears, okay, this is the one and this is the next one. So and then they are in constant touch with each other, they rotate together, and then this is a driven gear, means for input of mechanical energy we use a prime mover. Okay. From the prime mover normally we use electric motor as a prime mover. The one of the gear is driven gear. Okay. One of the gear is a driver gear, so which is in contact with the other gear, that is a driven gear here. Okay. When they are enclosed, okay, in a housing, and this is the inlet of the pump where the low pressure fluid enters at this point, and this is the outlet of the pump. Okay. So this is various components or construction of the external gear pump. Okay. Coming to the working principle of this gear pump. Okay. So when these two gears rotate, okay, so here at this point is where the two gears are come out of the mesh. Okay. That means to say the volume increases here. When the volume increases, we know that volume and the pressure are inversely proportional. So when the volume increases, pressure decreases. Okay. So here the fluid is inside the tank, the hydraulic tank, which is at atmospheric pressure because it is open to the or vented out to the atmosphere. And then when this volume increases, pressure decreases below this atmosphere, that we call it as a vacuum pressure. A pressure difference is created between the inlet of the pump and then the tank, which is at atmospheric pressure, because of which the fluid starts to flow into this region here, okay, at the inlet of the pump. After coming here, okay, as the gears rotate, the fluid is carried, okay, the space between the teeth and then the housing here, okay, these are the spaces where the fluid is carried, okay, and then they are thrown out, okay, at the outlet. So at the outlet where the two gears go into the mesh, okay, when the gears go into the mesh means the volume decreases, okay, since volume and pressure are inversely proportional, here the pressure increases, okay. So high pressure fluid that will go out into the hydraulic system, that will be used to do the various applications or the desired applications, okay. So basically the input energy, that means the mechanical energy which we give to the driver shaft, okay, with the help of an electric motor, is converted into the hydraulic energy or pressure energy or the fluid energy at the outlet of this one, okay. So basically we are using a gears and then they are externally meshed, okay. There are another type where the gears are internally meshing, okay. So that is internal gear, internal type of a pump, and this is a external gear pump. So coming to the second type of pump, that is under the positive displacement pump only. So this is called as a lobe pump, okay. So you can see here, okay, here something construction is similar to the both of these pumps, okay. Instead of gear here, okay, instead of these two gears, we use the lobes, okay. So and then coming to the construction, we have the two lobes here, and then inlet where the low pressure fluid from the hydraulic tank enters, and then at the outlet we have a high pressure fluid, okay, leaving into the hydraulic system, okay. So like they are enclosed, these two lobes are enclosed in the casing, okay. Coming to the working principle, it works exactly similar to that one, okay, exactly similar to the external gear pump. What is the difference between that external gear pump and lobe pump is that, so there we use the gears, here we use the lobes, and then there one of the like a gear is driver gear, means we connect one of the gear to the prime mover, whereas in this case both the lobes are driver, means both of them are connected to the prime mover, okay. So here both the gears are in constant contact with each other, whereas in this case they are not in constant contact, okay. There is a slight clearance between these lobes as well as between the casing and then the lobes, okay. That is the difference, okay. When this contact between the lobes doesn't exist, okay, that gives one of the advantage. What is that advantage is, it is very quiet, means in operation, that means it doesn't make much noise, okay, compared to the external gear where there are two mating gears, okay, there might be noises and vibrations coming into the picture, okay. So that is the difference between them. So in the similar fashion, when here at this point, inlet point, when the volume increases, the pressure decreases, which becomes a vacuum pressure less than the atmospheric pressure, but whereas the fluid in the tank is at the atmospheric pressure. So due to the pressure difference between the inlet of the pump and then the fluid which is in the tank, okay, the fluid starts to rise into the inlet, okay, and then they are carried, the fluid is carried in between these spaces, between the lobe and then the external the housing, okay, and then when it rotates it will release to the outlet here. So normally the low pressure fluid is converted into the high pressure fluid, okay. Here the lobes go out of the mesh, okay, that means the volume decreases, the pressure increases. High pressure fluid that is going into the hydraulic system or the fluid power system, that can be used to overcome the friction in the pipelines and then to do the desired application, for example lifting of the loads, etc. Okay, this is a sketch for the internal gear pump, okay. So coming to the construction of this internal gear pump, we have this inner gear and then we have the external housing. and then the inner gear is meshing with this the outer gear, okay, here, and then this is the inlet of the pump and this is the outlet of the pump, and along with this we have a crescent seal here, okay. So this inner gear and then the external gear in which it is meshing, okay, so they are not they are not concentric, okay, there is a little bit of distance between them. So coming to the working principle of this one, okay, as I said before, so in the case of the pump, due to the mechanical action, okay, one of the gear is driven, okay, by the prime mover, so because of which a vacuum is created. So the oil which is inside the tank, the hydraulic fluid which is at atmospheric pressure, okay, due to this difference in pressure, the fluid is drawn to the inlet of the pump here, okay. So this is the inlet, okay. So and then this crescent seal which acts between the seal between the inlet chambers and then the outlet chamber, okay. We can consider this portion as the inlet chamber, and then this shaded portion in the blue color, it is called as the outlet chamber, okay. So this acts as a separation between them. So when this internal gear is driven by the prime mover, okay, so due to the mechanical action, the volume increases and the pressure decreases at the inlet, okay. So below the atmospheric pressure, that is vacuum pressure, due to the pressure difference, the fluid is taken into this chambers here, okay. So between this internal gear and then these spaces, okay, so the fluid is taken and then which is discharged at the higher pressures, okay, at the outlet here, okay. So the purpose of having this crescent seal is that it will separate the inlet and discharge ports. So coming to the last type of pump, which is a gear pump. In the case of a gear pump, it is a G rotor pump, okay. So in this coming to the construction of it, which has a G rotor element and then a female gear rotor, so which are in constant mesh with each other, and then we have a casing which encloses whole of this, and then a discharge port, and then this is the inlet port here, okay. So when this either of the gear is driven, okay, so the suction is created because the vacuum pressure is created which is below the atmospheric pressure, due to which the oil is drawn to the inlet port of this G rotor pump, okay. And then this oil is carried in between the space of this a female gear rotor and then the G rotor elements. As this rotates, whatever the fluid which is carried in between these two elements is discharged at higher pressure to the discharge port, okay. So that is how the working of this G rotor pump happens, okay. That means conversion of mechanical energy into the hydraulic energy, okay. So these are. Now let us solve some of the numericals which are based on the gear pumps, okay. So that is we need to first derive some of the expressions for the volumetric displacement and then theoretical flow rate as well as the volumetric efficiency. In order to derive this volumetric displacement, or in order to write this the expression for volumetric displacement, we need certain parameters. So that is, the first one is d naught, that is outside diameter of gear teeth. So normally which is expressed in terms of the meters, and then we need di, that is inside diameter of the gear teeth, that is inside diameter of the gear teeth, that is also expressed in terms of the meters. So we need the capital letter L, that is the width of the gear teeth. So that is capital L is equal to width of the gear teeth. So that is also expressed in terms of the meters. So along with this we have Vd, capital letter V suffix d, that is volumetric displacement. Vd is equal to volumetric displacement, that is expressed in terms of meter cube per revolution. So and that is next is Qt, that is Q suffix t, that is theoretical flow rate. theoretical flow rate, that is in meter cube per minute. And then we need one more parameter, that is capital letter N, that is revolutions, number of revolutions per minute. So capital N is equal to RPM of the pump okay. So these are the various parameters we need to look at okay. So that is D naught is outside diameter of the gear teeth, and then Di is the inside diameter of the gear teeth, whereas L is the width of the gear teeth, and then Vd is volumetric displacement, that is expressed in terms of meter cube per revolution, and theoretical flow rate, that is meter cube per minute, and then we have N, that is RPM of the pump okay. So we have one more term, that is nu V, so that is volumetric efficiency. Nu V is volumetric efficiency okay. So let us try to write an expression for the volumetric displacement of the gear pump. So the volumetric displacement is given by so the volumetric displacement is Vd is equal to pi by 4 times d naught square minus of di square, which is whole thing is multiplied by L okay. That is d naught is outside diameter of the gear teeth, di is the inside diameter of the gear teeth, and then we are multiplying that with the length of the gear teeth okay. This is the expression for the volumetric displacement okay. So next is we need to write the expression for a theoretical flow rate okay. So the theoretical flow rate is given by theoretical flow rate Q suffix T okay. So the theoretical flow rate is the Qt is equal to so Vd times N okay. So it is a multiplication of volumetric displacement times the number of revolutions of the pump okay, or the speed of the pump okay. So if you look at the units okay, Qt is expressed in terms of so meter cube per minute, and this Vd is expressed in terms of meter cube per revolutions. So we know that the speed is expressed in terms of revolutions per minute okay. So these are the two expressions we need in order to solve the problems, that is one is volumetric displacement, which is given by Vd is equal to pi by 4 d naught square minus of di square into L, and then theoretical flow rate, that is Q suffix T is equal to Vd into N, that is volumetric displacement multiplied by the speed of the pump okay. So next is one more important expression we need is the volumetric efficiency of the pump okay. So the volumetric efficiency which is normally written as nu V. So that is nu V is equal to, it is ratio of actual flow rate to the theoretical flow rate okay. So that is the expression for volumetric efficiency okay, QA divided by QT okay. So these are the three expressions we need to know for solving the numericals which are for the gear pumps. Now let us solve a problem which is based on the gear pump. That is, the problem is a gear pump has a 75 mm outside diameter, a 50 mm inside diameter, and a 25 mm width. If the volumetric efficiency is 90% at rated pressure, what is the corresponding actual flow rate? Okay, the pump speed is given, that is 1000 rpm okay. Here the unknown what we have to find out is the flow rate of the pump, that is actual flow rate of the pump okay. So let us list out what is the given data. So the given data is Okay, gear pump has a 75 mm outside diameter. The outside diameter is given, that is represented by d naught is equal to 75 millimeters. If you convert that into the meters, you will get it as 0.075 meters. The inside diameter, okay, of the pump is 50 millimeters. Okay, so that is di is equal to 50 millimeters. So if you convert that 50 millimeters into the meters, you will get it as 0.050 meters. So, and then the width of this pump is given. Okay, so that is equal to 25 mm. Okay, so L is equal to 25 millimeters. So which is equal to 0.025 meters. So if the volumetric efficiency is 90%, okay, the volumetric efficiency is given, so that is represented by nu V is equal to 0.9, and what is the corresponding actual flow rate? That is QA is equal to question mark, that is we need to find that out, and then the pump speed, okay, that is in RPM, that is capital N is equal to 1000 RPM, which is given. So this is the given data, d naught, which is 75 millimeter, 0.075 meters, and di, that is inside diameter, that is 50 millimeters. If you convert that into the meters, so you will get it as 0.05 meters, and then L, that is width of the pump is, or the gear teeth is 25 millimeters, so that is 0.025 meters, and then volumetric efficiency is 0.9. QA, that is what we have to find out, that is the actual flow rate. So and then we have the speed of the pump, that is 1000 RPM. So in order to solve this, okay, we need to find out the volumetric displacement. Okay, so that is volumetric displacement, which is represented by VD. So we know that the formula for volumetric displacement is Vd is equal to pi by 4 times d naught square minus of di square, which is multiplied by L. So which is equal to, if you substitute the values, so which is equal to pi by 4 times what is d naught square, that is 0.075 whole square. Okay, so this is equal to 0.075 whole square minus of what is di square, that is inside diameter is 0.05. So this is 0.05 whole square. Okay, so which is multiplied by L. Okay, that is the width of the gear teeth, so that is 0.025. So if you simplify this, you will get this Vd is equal to 0.00040 zeros and then 614. The units for volumetric displacement is meter cube per minute. Meter cube per revolution. So this is the volumetric displacement of the pump. Okay. So once you know this volumetric displacement, from that we can find out the actual flow rate, that is QA. Okay. So for that we know that the volumetric efficiency okay, so is given by, so nu V is equal to actual flow rate, that is QA, divided by theoretical flow rate, that is QT. So if you simplify this, so we need this QA. Okay, so QA is equal to nu V times of QT. So I will write it here. So QA is equal to, so nu V times of QT. Okay, so then this is equal to nu V times, I can write this QT, that is theoretical flow rate, as it is the volumetric displacement times the speed of the pump. So that is N, capital N. Okay, so if you substitute the values here, so we know that volumetric efficiency it is given in the problem, that is equal to 0.9. And then the volumetric displacement, okay, so that we have find out in the previous calculations, that is 0.000064, okay, so 614 times what is N, that is capital N, that is the speed of the pump, that is 1000 RPM, okay, so 1000. So if you simplify this, you will get this actual discharge as 0.0553, okay. So what is the units for this? It is meter cube per minute. Okay, so that is how you find out. So when the all the parameters are given, that is outside diameter, inside diameter, and then the width of the gear teeth, okay, and then volumetric efficiency is given. First you have to find out the displacement volume or the volumetric displacement in meter cube per revolutions. After that, using this formula for efficiency, so you can find out this actual discharge or the flow rate. Thank you.